Hello students, welcome to the session, and we are into the third session of organic series which we started. And in the last session, if you could recall, we talked about the chemical bonding required for the making of organic compounds. So now it is a good time to introduce another important topic which we have not yet discussed with you people, is the topic of catenation. So before I go into the discussion of this particular thing, let me recap what we did in the last session. So we talked about the chemical bonding that is pertaining to organic compounds, that too of the type covalent bonding. We talked about that hydrogen and fluorine always join with somebody through a single covalent bond because they are in a requirement of one electron only. So that is why we said it as to be monovalent species, if you could recall, and these always would attach from the terminal of a compound. Then we talked about oxygen. Oxygen is in search of, oxygen already is having 6 electrons with it, and it is in search of 2 more electrons. So the 2 more electrons it can get with somebody by taking 2 electrons through the single bond or with one double bond. So that is why we said it divalent. I hope you are recalling all this. And similarly, we talked about nitrogen is a trivalent, and we said carbon to be tetravalent, if you could recall. And this we have done in detail, and we said that carbon can join by 4 single bonds or one double, 2 single, 1 triple, 1 single, or 2 double bonds. And also we said it like this, although we haven't yet done the advanced level of chemical bonding. We said all of these bonds which we have shown with the carbon or for any element, these are sigma bonds. And wherever you get double and triple bond, in the double bond, one bond is pi, another all are sigma. And similarly, here you have 2 pi and 2 sigma, here you have 2 sigma and 2 pi, if you are recalling it. So this is what we have done in the last time. Also, we talked about how to interpret for a stable organic compound, if it is having even number of electrons, how to find the number of covalent bonds. So this trick I have shared it with you in the last session. That number of covalent bonds you can get with electron demand minus electron supply divided by 2. And for hydrogen, because hydrogen is in search of one more electron to have a octet of helium, so its electron demand is 2. And that for other elements of the other elements which we require in the organic chemistry, like carbon, nitrogen, oxygen, fluorine, all of these are in a demand of 8 electrons. Just like if I would say for carbon is having 4 valence electrons, so it is in search of 4 more electrons so that it could become a octet complete of 8 electrons. So all other elements would be requiring the 8 electrons as their electron demand. And electron supply, we said it, the number of valence electron in for a given element. This we have already shared with. Let me give one example and then we'll continue with the topic which we are supposed to do today only. So if you have given this formula, say for example, and you are supposed to find the number of covalent bonds, we said that the electron demand is 8. There are 2 carbon atoms. If you could see, there are 2 carbon atoms, they are looking for 8 electrons. And there are 6 hydrogen atoms, they are looking for 2 electrons to have a duplet complete because they want helium configuration. And oxygen is in search of 8 electrons because it is again having 6 valence electrons, so it is requiring 2 more to get the octet complete, and that is why we are saying its electron demand is 8. And here we have written all the valence electrons required. For carbon it is 4, for hydrogen it is 1, for oxygen it is 6. So in totality, if you calculate it out, so the number of covalent bond we get with 8. Now this particular compound would be having 8 electrons. If it is having 8 electrons, how is it to be placed? 8 bonds it would be having, and how these bonds would be placed with, because as you know for sure, this is being done in detail in the last session. So those who are new, please just go through the last session which was in length. Do it in a 2x speed if you find it is little slow, so you can, and that is the benefit of YouTube, you can go whichever way you would want and at whatever time you want to see the lectures. Now see here, as I was saying, C2H6O, how you have to create 8 covalent bonds. We get with the formula, it is having 8 covalent bonds, and now we are very sure that carbon is always would be in the somewhere in the center, it is never be a terminal one. Hydrogen is always terminal. Oxygen can join with somebody either with 2 single bonds or 1 double bond. Now which way it would join, this is coming in the next lecture, that how you can interpret from the formula that would this oxygen be joining in this compound through single bond or 2 single bonds or 1 double bond. This trick I will let you know in the next session. But at the moment, we just would write that carbon can join it like this. Is it okay? And if I place hydrogens like this, you would get with the answer. And now you know oxygen can join with single bonds. And the other student can write it like this as well, that if he or she happen to write it like this, this also could be the structure, because around carbon there would be 4 bonds either in form of single bonds, double or triple, but in this case it is through the single bond. So this is what we achieved here with this is what we get. And this I told you last time also, this particular species can also be written as, this is the condensed form of writing the same thing. So this is called as ethanol, and you can write it like this also, CH3OCH3. So these two then would be said as isomers, because the molecular formula is same. So this is the beauty of the thing. Now this is a good time to introduce this term, which I have not yet said about, that what is the unique property of carbon. Other than high melting and boiling point in the last session, which we have talked about, that how beautiful is, probably in the first session I talked about the carbon's high melting and boiling point. But other than that, it's having a very unique property, which we call it as catenation. Catenation in itself is a self-linking property. Self-linking property. Now we are having a good understanding of the fact that compounds of the carbon, because we just have seen that carbon would join by any of these permutation combination, and it can join with any of these heteroatoms as well. So it can do the self-linking as well as it can join with the heteroatom through multiple bonds. So that is why it tend to form long chains, or there are lot many permutation combinations possible for the fact that it do show self-linking property. And this self-linking property, if I just dig deep into it, what is the cause of the self-linking? The cause of self-linking is these 2 points, which we have already endorsed with, that is tetravalency. Carbon would always want to keep itself tetravalent. So this we will address something more about this tetravalency in terms of hybridization through the valence bond theory after we complete the IUPAC naming. So advanced level of chemical bonding I will take up little later. And when we talk of multiple bonding, carbon can do effective multiple bonding with its own carbon atoms or with heteroatoms as well, like carbon nitrogen can combine like this. Carbon can combine with double bond or triple bond with nitrogen, or with double bond also with nitrogen. It can join with double bond with, so this double and triple bond happens to be said as to be multiple bonds. And the cause of this multiple bonding is the small size of carbon it can do. So this many of you people would not understand at this point of time, although I am going to write it. The cause of effective multiple bonding is effective pi bonding. As we said last time also, this sigma and pi we will be discussing in little more depth after we complete the IUPAC naming. Then the advanced level of bonding would come. Effective pi bonding means that those atoms which are small in size, they can effectively make multiple bonds with its own atoms or with the heteroatom, and carbon does this property very beautifully. So the cause of catenation, is self-linking property. And what is its cause? The cause is, you can say, the tendency of carbon to keep itself tetravalent and to do effective multiple bonding. And effective multiple bonding it can do with its own atoms as well as with the heteroatoms. So now we would be very clear with the thing that carbon, because of this virtue, just like if I would show that if I just would make something like this, so it can keep on becoming a long chain. Only thing is you have to keep it tetravalent. That Around carbon there must be 4 bonds. That 4 bonds can be in form of 4 single bonds, 2 single, 1 double, and 1 triple, 1 single, or you may say it as on both sides you have double. So you have to keep the tetravalency intact. So here you have 4 bonds, here 1 2 3 4, so 4 bonds are again there in this. And similarly you can go for this carbon also. This carbon is also having a 4 bonds, 1 2 3 4, and this one is having 1 2 3, and I have to place one more hydrogen. Next time in some probably in 1 2 more lectures we will be also going to address the shape of these molecules, how these are oriented in space. This is a simple bond line this is simple. Let me show it to you. This is one of the very good book of organic chemistry, Graham Solomon. I find this diagram very interesting. So we will be very soon would be explaining the things in the ball and stick model as well. So this part we have done with, if you are recalling, this we have already done. And we also have spoke about the dash formula. So this representation is a dash formula. This is not the exact how the molecule is looking in the space. That is not there. That is being shown by ball and stick model. We will be answering it. And this is the condensed formula. And this is the bond line formulation or bond line representation. For this, I am going to speak a bit more so that you now would feel comfortable, because I would be very often using this type of a representation, because by making this type of representation again and again, it is going to take a good amount of time. So let me explain a bit more about this representation. What I am going to say it about is bond line representation. This representation is a dash, just like here it is written dash formula representation. So you are just showing it with some dash. And many of times this is a very basic one, but we would be saying it now through the bond line representation. Now what exactly is bond line representation is that the number of carbon atoms here are 3. So I will make 3 lines, and all these corners are having carbon, as simple as that. And there is no need of putting up any sort of or showing any hydrogen into it. If you just would represent it like this, what does this mean? It means there are 3 carbons. All these are showing 3 carbons. And this is by default understood that since I have not shown any double or triple bond in this representation, so it means there are that much number of hydrogen atom there in it to complete its octet. So what we are saying is there are 3 hydrogen here, 3 and 1, 4, 1, 2 and 2 more hydrogen. So it makes it 4. So this is 1 and 3 more. So it is propane. I just would not want to speak the name, because naming I will be doing after 2 more lectures. So similarly, if I would go for this, here you can see there are 3 carbon atoms. You can very well see there are 3 carbon atoms. So these 3 carbon atoms can be shown it like this also. This is the condensed formula, CH3, CH2, and this is what we can represent it like this. And in terms of bond line representation, I will show it like this. This is 1 carbon, another 3 carbons are there. But here I have to mark it with oxygen. So let me draw it once more like this. So whatever is the number of hydrogens are there, they are well taken care of. How it is being taken care of? If I just would go the reverse way to show it, there are 3 carbon atoms, 3, 1, 2, 3, and we are showing here you have a double bond oxygen. Now to complete the tetravalency, you have to place the hydrogens. So here you have, I can do it like this, 3 hydrogens, 3 and 1, 4. And now if I would show 1, 2 and 2 more, so it becomes CH2. And here how many bonds we have? 1, 2, 3 and 1 more, 4. So this way it is to be shown. So this representation which we have shown it like this or this is called as bond line representation. And this is what you call it as condensed formula. And this is a dash formula representation of a organic compound. But none of this is actually representing the exact shape of these molecules in space. For that, you have to wait for another 1-2 more sessions. we will be addressing that too also. Now, just like in this case, if I would show CH3, it is joined to oxygen. This is CH2 and this is CH3. I think it is very clear. This is CH3, this is CH2, and this is CH3 along with the oxygen. Now, if I have to show it with the bond line representation, I will simply mark it like this. This is one carbon, and this dots which I am putting up here is actually not being shown to. This is I'm showing just to make you feel comfortable. I just would represent it like this. Okay, and along with it also you should make this or develop this habit of showing the lone pairs present on a heteroatom. Just like in oxygen you have a lone pair available. So this in a way shows or strengthen your subject if you have developed this habit of representing the lone pairs. Just like here you have two lone pairs, and here also you have two lone pairs, and there are two bond pairs. Is it okay? So this is good to show the lone pairs on the oxygen or any heteroatom. Similarly, if I would go for this one, so there are how many carbon atoms? 1, 2, 3, and this is nitrogen. And this nitrogen do also have a lone pair. And now you could see, I can write it like this: CH2 double bond CH, CH2 NH2. This is the condensed formula. And if I have to write it in the bond line representation, so this would be 1, 2, 3. There are 3 bonds, but this here I would not be showing any carbon. So this is very tricky and very important. Here you have to directly write the heteroatom like this. So this in a way shows 3 carbon atoms, and here you have a double bond. So this is the representation to be placed. Many of times students do this mistake. They do it like this, that they generally do a mistake by showing a extra carbon. So this is not to be shown it like this. So you have to be very careful while choosing the structure. Okay, so lone pair also is to be mentioned here. So not a tough one. So similarly, if I have to do this one, so this is one carbon, which is, this is the second carbon, this is the third carbon, this is the fourth carbon, this is the fifth carbon, this is the sixth carbon. Now also you have to see here is, this is CH3, because all of these at least are bonded by a single bond, and here it is being shown triple bond, so you have to place a triple bond, and there are 4 bonds already done with. Here you have to place CH2, here CH double bond CH2. Now you have to represent it in the bond line representation. I am not here choosing any sort of way of selecting the chain. I am just representing there are how many carbon atoms? 1, 2, 3, 4, 5, 6. So there are 6 carbon atoms. So I will place it like this. So this is 1, 2, 3, 4, 5, 6. This is this number line you have not to consider it, that which way the number lining has to be selected with. That rules and regulation we will do in the IUPAC naming. So here I am just representing that between 2 and 3, between this and this, I am having a triple bond, because all of these corners of the carbons, which dots I am just making it just to make you comfortable with. And here you have a double bond. Now let us do the reverse way also. That reverse way, that if this structure is being given, how is it to be shown? So there are 3 carbon atoms. I just would write 3 carbon atoms. So simple it is. And between this you have a double bond. And now you have to place all the hydrogens to complete the octet. So here 1 and 3 hydrogens. And this is already complete. 1, 2, 3, 4. It is already complete. And here also you would get 3 hydrogens, because this is 1 and 3 hydrogen. So this is acetone, by the way. And similarly, if I go for this one, so these are the 4 carbon atoms, which you should mark it like this, 4 carbon atoms. And between second and third, between this and this, if you could see here, you could see a double bond. So I just would place a double bond here. And on the last carbon, which I'm marking it with blue, here you find oxygen OH. And rest of the hydrogens is to be placed by seeing the calculation in terms of tetravalency. So 1, 2, 3, 4. So 3 CH3 it becomes. Here you have how many bonds with you? Here we have almost 1, 2 and 3. So that means there is one more hydrogen is going to come here. Similarly here also. And here you have already have all the 4 bonds intact. So this is the way it is to be done. And as I said, always make or develop this habit of placing the lone pairs. So oxygen would have lone pairs like this. They can simply ask you how many lone pairs are there in this formula. So this is you have to deal with. Another cyclic form also we will take up two more examples here in the form of cyclic. So if I have this structure, so every corner is a carbon as a simple statement. All these corners are nothing but carbon. So I just would write CCC, and you would not be seeing any double or triple bond. So we would be placing hydrogens required here. So now here you not to worry about this fact that which way the hydrogens are shown, because this is a bond line, this is a simple dash formula, whichever way you write, there is no issue. When we are showing it in the form of ball stick or three-dimensional way, then we have to be little particular about in terms of that shape should look like the way it is having actually in the space in the slide also, or onto the drawing onto the copy, it should look like that one. So here I can say it like this also, this CH2, CH2 and CH2. So similarly, if I will do it like something like this, say for example, you are being given like this. So how many carbons you could see here are 5 carbons, 1, 2, 3, 4 and 5. And between two carbons you have one double bond shown here. So I would just place a double bond here, and say for example if there is one more double bond here, so I have to place it like this. And now you have to place the required number of hydrogens. So here I could see 1, 2, there are 2 bonds already there, so there are 2 hydrogens. Similarly here you have 1, 2, 3 and this is 4. Similarly here also 4, here also 4, here also 4. So I can show it like this also, CH2, CH, double bond, CH, CH, double bond, CH. So this is beautiful. So if you keep on drawing it like this, you will feel so thrilled with, because you can make any number of compounds of the carbon just only thing is you have to keep the things tetravalent. As is in the first lecture I shown you from the book of Claydon, that if you have 30 carbons, there are almost 10 raised to power 63 permutation combinations which can generate out of that 30 carbons. So many formulas can be generated. So that in a way shows such a beautiful thing into the organic chemistry, and that is what my endeavor is to start with. So to begin with, I am showing you that rather than going into the IUPAC naming directly, I am making you feel that how interesting is organic, that from a given formula you can generate so many structures, and all of these structures, if their formula is same, they are isomers. And that is where we have to learn the things, that what is the name of these isomers, what are the functional groups, and so and so forth. So there is another compound which is very popular in organic chemistry, is cubane, just because it just like look like a cube. So all of these corners are nothing but what? These are carbons. Now if I just would write all of these as carbons, now can you figure it out that how many let me show it, how many hydrogens do you have in this? How many hydrogens do you have in this? Because every carbon is bonded to 3 carbons. If you could see 1, 2, 3, I'm showing you this one. So there is 1 hydrogen available here. Similarly, on every side you have 1 hydrogen, isn't it? There is 1 hydrogen. There is 1 hydrogen. And this particular molecule I will take up in the next session also. So in a way, this is C8H8, which is a very popular compound which we call it as cubane. So I hope you have gone through. Okay, let me take one more example. So here you could see how many carbon atoms are there in this compound. So I could see very well 4, 5 and 6. So there are 6 carbon. So this you can show it like this. Now it is at your discretion, whichever way you feel comfortable with. Same formula I can draw it like this also, because let me show the first the hydrogens. How many hydrogens do we have here? CH2, because there are 2 bonds, CH2. This is also CH2, this is also CH2. But here you have 3 bonds already. So there would be 1 hydrogen, 1 hydrogen. Is it okay? So what I was saying is that you, if I just would mark it like this, 1, 2, 3, 4, 5. Is it okay? So there are 5 carbon atoms. You can show it like this, and 1 and 3 are joined by 6. So you have not to worry about the fact if I just would write, because this is the representation. It is not the actual structure, three-dimensional structure we are not discussing about. So if I just would mark it like this, somebody mark it like this, 1, 2, 3, 4, 5, and you are saying 1 and 3 are joined through 6. So I can show it like this also. So these all are same. So any representation you can go for. And similarly for this one also, this is your homework. Try this out and just show me what is the formula, what is the value of x and y in this formula. So do it for me and write it onto the comment if you would find it right. And lastly, which many of students do a mistake here, is that they simply would ask me many times that, sir, if there is some formula like this, CH3, CH2, 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 CH3, should we, so how many carbons I have taken? I have taken 6 carbons with single bonds. So I can show it like this, 1, 2, 3, 4, 5, 6. At times you can see, you would see in your books shown it like this also. So there is no issue. 1, 2, 3, 4, 5, 6. I took one more. So I should rub it here from. Oh, it went wrong. Okay, let me draw it once again. So what I was saying is that I can go it like this, 1, 2, 3, 4, 5 and 6. So this again is the same thing, or someone wrote it like this, say for example 1, 2, 3, 4, 5. So this is 1, 2, 3, 4, 5, 6. So this is same, this is same, this is same. Or as a matter of fact, if you would write it like this, 1, 2, 3, 4, 5, 6, this also is. But the ideal way of representation is this, but other ways, every only point is every corner is representing a carbon, and whatever hydrogens are required there are there in that formula. So if I would write someone wrote it like this, say for example. So if I would say, you can make it like this, any number of carbons. So what way we have to represent it? You just have to see how many carbons we have taken, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I just mark the 9 carbons like this, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So how many hydrogen, there is a triple bond, 1, 2, at the second position you have a triple bond, 1, 2, so here is a triple bond. And if I go further, 3, 4, I'm here not marking any sort of, I'm not telling you any sort of what I would say numbering. I'm just making the compound from the bond line representation. So 1, 2, 3, 4, 3, 4, 5, 6, 7, 8, 8 and 9. So what you are able to see it, that on the 7th carbon you are finding something in terms of double bond. So here you have a double bond, and that double bond is also a carbon, so that is CH2. And also you would see it on to the 9th one also, or CH2, or I can make this as 10 also, as a matter of fact. So this is the way, and now you have to place all the required number of hydrogens. So here you would get 3, it is already 4. So here you have CH2, CH2, CH2. This is already 4, CH2, this is requiring 1H. So this is the way it is to be done with. I hope you have understood 3 things we talked about today in the session about the catenation and how to show different ways of representation of organic compounds. If you liked it, do comment this thing, chemistry with Gurpreet Sir or organic with Gurpreet Sir. It would help me reach more people. Thanks a lot. Have a nice day. Would be seeing you in the next session, where we will be talking about very important topic which you would not miss. Most important topic, I would say, in the upcoming session. I'm not naming it just to keep the curiosity intact. Bye bye, take care, have a nice day, stay safe.